Hello everyone. This is a beginning of new chapter, coordination compounds, also called as complex compounds. We will see the learning objectives at the end of this video. First, let us try to understand what is meant by a coordination compound and how these are different from covalent or ionic compounds that we have discussed earlier. We have earlier seen various ionic compounds formed by main group elements such as sodium chloride and aluminum chloride, etc. We have also learned that 1 mole of sodium chloride upon dissolving in water produces 1 mole of Na plus and 1 mole of Cl minus ions. Similarly, 1 mole of aluminum chloride upon dissolving in water produces 1 mole of Al3 plus and 3 moles of Cl minus ions. Now, let me ask you a question. What kind of experiments or measurements can prove that the above compounds dissociate as mentioned? Think about it. There are two different kinds of experiments that we can do. One, we can measure the electrical conductance of the solution by dipping electrodes in the solution. And based on the conductance data, we can predict the number of moles of ions floating in the solution. The second way to do this is we can precipitate all the Cl minus ions by adding excess of Ag plus ions. And then we quantify the amount of silver chloride formed. Based on the number of moles of silver chloride precipitated, we can calculate the number of moles of Cl minus ions present in the solution. Scientists working on the salts formed by transition metals found out some interesting dissociating patterns. Alfred Werner, a Swiss chemist, studied a series of compounds of cobalt-3 chloride with ammonia. The following are the molecular formulas of the compounds: COCl3 6NH3, COCl3 5NH3, and COCl3 4NH3. He made several observations about these compounds. First, these three compounds are bright and colorful, unlike most of the ionic compounds from main group elements, which are white in color. In addition, these three compounds have different colors. The first compound is yellow, the second one with 5 ammonias is purple, and the third one with 4 ammonias is green in color. Next, he wanted to find the number of dissociable Cl minus ions in these compounds. From the formulas, it looks like all the compounds have 3 dissociable Cl minus ions per formula unit of the compound. To test this hypothesis, he dissolved 1 mole of each of these compounds in water and added excess of silver nitrate, which produces Ag plus ions, to the solution. He expected that all three compounds should precipitate 3 moles of AgCl. And to his surprise, he found out a completely different result. The first compound gave 3 moles of AgCl, the second one gave 2 moles of AgCl, and the third one gave only 1 mole of AgCl precipitated. That is, even though all three compounds have 3 chlorine atoms per every formula unit of the compound, the first compound produced 3 ionizable Cl minus ions, the second compound produced only 2 ionizable Cl minus ions, and the third compound produced only 1 ionizable Cl minus ion when dissolved in water. The next question is, why? Scientists have to come up with a theory to explain these observations, and Alfred Werner did exactly that. He called these compounds coordination compounds or complex compounds, and he proposed the theory of coordination compounds. The following are the postulates of his theory. 1. The transition metals in the coordination compounds form two types of bonds, or he called them as valences: primary valence and secondary valence. He said that the primary valences are ionizable, and these are satisfied only by negative ions. Any anion can act as a primary valence. For example, chloride ion, sulfate ion, nitrate ion, etc. The number of primary valences in a compound gives us the oxidation number or oxidation state of the metal. On the other hand, the secondary valences are non-ionizable, and these can be satisfied by neutral molecules and or negative ions. The number of secondary valences in a coordination compound is equal to the coordination number of the metal. The examples of species that can form secondary valences are chloride ion, ammonia, water, etc. Next postulate. When writing the formula of a coordination compound, we use a specific format. The secondary valences along with the metal ion are shown inside square brackets, which represents that everything inside the square bracket is non-ionizable and acts as a single entity. The primary valences are shown outside the square bracket, and they ionize when dissolved in water. Based on these postulates, Alfred Werner tried to explain the observations of the earlier experiment and write the compound's formula in a proper format. The first compound produced 3 ionizable Cl- ions, which means that these 3 chlorines should be primary valences, and they should be placed outside the square brackets. The metal ion cobalt, and along with 6 ammonias, which are the secondary valences, should be inside the square bracket. This is the formula of compound 1 in proper format. It is important that you learn the differences between the primary and secondary valences and how to calculate them from a given formula. The primary valence is now called as oxidation number of the metal ion, and the number of secondary valences is called as the coordination number of the metal ion. First, let us calculate the oxidation number of cobalt. Earlier in the course, we have learned how to calculate the oxidation number of an atom in a compound. We have 1 cobalt, and let's assume that its oxidation number is X, plus we have 6 nitrogens, and when nitrogen is with non-metals, its oxidation number is -3, plus we have 18 hydrogens. When hydrogen is with non-metals, its oxidation number is +1, and then we have 3 chlorines, and chlorine's oxidation number is -1. If we add up all the oxidation numbers, we should get 0, which is the net charge on the compound. If you solve for x, we get x is equals to +3. This is the oxidation number or primary valences of cobalt in the compound. There is an easier way to do this. We know that ammonia is a neutral molecule. That is, the overall charge on the ammonia is 0. Therefore, instead of adding the oxidation numbers of 6 nitrogens and 18 hydrogens, we can treat ammonia as a group of atoms with a net oxidation number of 0. That is, we have one cobalt, and let's assume its oxidation number is X, plus 6 ammonias, and each ammonia has an overall charge of 0, plus 3 chlorines, each of them have -1 charge. These should add up to 0, and if we solve for X, we get X is equals to +3. So, how to identify a primary valence in a given coordination compound? Any anion present in the compound is contributing to the increase in the oxidation number of the metal. Therefore, it acts as a primary valence. We have 3 chlorines in the compound, and each of them is increasing the oxidation number of cobalt by +1. Therefore, all 3 chlorines are primary valences. Next, let us calculate the coordination number. Coordination number is the number of secondary valences, that is, the species present inside the square bracket. We have 6 ammonias, therefore the coordination number is 6. The second compound produced 2 ionizable Cl- ions, which means that these 2 chlorines should be primary valences and they should be placed outside the square bracket. 5 ammonias and remaining 1 chlorine act as secondary valences, and along with the metal ion cobalt, they should be placed inside the square bracket. The oxidation number of cobalt can be calculated like we did before, and it is same as before, that is +3. Note that the secondary valence or coordination number is still 6. The chlorine inside the square bracket acts both as a primary valence and secondary valence. Secondary valence because it is inside the square bracket, and primary valence because it is negatively charged and therefore it is increasing the oxidation number of cobalt. We have seen in the previous slide that the oxidation number of chlorine is -1. Therefore, each chlorine increases the oxidation number of cobalt by +1. And anything that increases the oxidation number of the metal is a primary valence. Let's now look at the third compound. The third compound produced only 1 ionizable Cl- ion, which means that only one of the chlorines should be a primary valence and it should be placed outside the square bracket. The 4 ammonias and the remaining 2 chlorines act as secondary valences, and along with the metal CO should be inside the square bracket. The oxidation number of cobalt can be calculated like before. It comes out to be +3. Again, the coordination number of cobalt 3+ is 6. The 2 chlorines inside the square bracket acts both as primary valence and secondary valence. Let us now learn some definitions and some important terminology regarding a coordination compound. The transition metal in the coordination compound is called as the central metal ion. The molecules are ions that are inside the square brackets and are satisfying the secondary valence are called as ligands. In this example, we have 5 ammonias and 1 Cl- acting as ligands. The central metal ion, along with the ligands that are inside the square bracket, is called as coordination sphere or complex ion. As we discussed earlier, this compound, when dissolved in water, it produces two Cl minus ions and one complex cation with a formula CO, NH3 taken 5, Cl, and with a net charge of 2 plus. The complex ion does not dissociate further in water. It acts as a single entity similar to a polyatomic ion. Let us now discuss a little bit about the type of bonding in coordination compounds and why these compounds are called coordination compounds. In other words, we learn how the primary and secondary valences are bound to the central metal ion. We learned earlier that this compound, when dissolved in water, produces two Cl minus ions and a complex cation. So the question is, why only two of the Cl minus ions are ionizable? And the way the secondary and primary valences are bound to the central metal ion can answer this question. The secondary valences, also called as ligands, in this case we have 5 ammonias and 1 Cl minus ion. These are bound to the central metal ion by a special type of covalent bond called as coordinate covalent bond. And that is why these compounds are called as coordination compounds. Now, what is a coordinate covalent bond and how it is different from a regular covalent bond? In a regular covalent bond, each of the participating atoms contribute one electron, and the electron pair formed is shared between both the atoms. In contrast, in a coordinate covalent bond, one of the participating atom contributes two electrons, that is one pair of electrons, while the other atom contributes 0 electrons, and the electron pair is shared by both the atoms. While a covalent bond is represented by a straight line, a coordinate covalent bond is represented by an arrow pointing from the donor atom, which donates its electron pair, to the acceptor atom, which accepts the electron pair. So, for a coordinate covalent bond to be formed, there should be a donor atom which consists of a non-bonding electron pair or lone pair that it can donate, and the acceptor atom should have an empty orbital to accept the electron pair. In this example, each of the 5 ammonias and 1 chloride ion are the ligands. These ligands act as electron pair donors, and the central metal ion is the electron pair acceptor. For a molecule or ion to act as a ligand, it should definitely have a lone pair. Otherwise, it cannot form a coordinate covalent bond. In this example, both ammonia and Cl- have a lone pair, which they can donate to the central metal ion. These ligands bound to the central metal ions are non-ionizable because they are bound to the central metal ion by a coordinate covalent bond which is similar to covalent bond. So, the secondary valences are bound to the central metal ion by a coordinate covalent bond. Then how are the primary valences bound to the central metal ion? We have 3 Cl- ions that satisfy the primary valence of the central metal ion. These 3 Cl- ions are bound to the central metal ion by electrostatic force of attraction between an anion and a cation. That is, they are bound by ionic bond. And that is why the primary valences are ionizable in water. We have already discussed 2 different types of definitions for acids and bases. Arrhenius acids and bases, and Bronsted-Lowry acid and bases. Here we are about to discuss a third definition of acid and bases proposed by a scientist named Lewis. Lewis defined an acid as an electron pair acceptor and a base as an electron pair donor. Therefore, the central metal ion in a coordination compound is a Lewis acid and the ligands are Lewis bases. The reaction between the central metal ion and the ligands is an acid-base neutralization reaction. Let us now discuss types of ligands. Ligands are classified into different types based on the number of donor atoms present inside the ligand. Monodentate ligands have a single donor atom. Bidentate ligands have two donor atoms, each of which bonds to the metal ion. Polydentate ligands have more than two donor atoms, each of which bonds to the metal ion. Let us see some of the examples of monodentate ligands: water, Cn-, SCN-, NH3, Cl-, etc. Notice that all the ligands have a lone pair or non-bonding electron pair that can be donated. Next, let us look at some examples of bidentate ligand. Ethylene diamine. We have two nitrogens, both of them have a non-bonding electron pair and that can be donated to a metal ion. Next, oxalate ion. Both of the oxygens have lone pairs which can be donated to the central metal ion. Next, let us look at an example of a polydentate ligand. Ethylene diamine tetraacetate is an important hexadentate ion. That means it has 6 donor atoms, each of which can donate an electron pair to the central metal ion. Bidentate and polydentate ligands give rise to rings in the complex ion structure. A complex ion containing this type of structure is called as a chelate. The word chelate is derived from the word chele, which means claw. And the reason we call these structures chelates is because the ligand appears to grab the central metal ion like a claw. Let us do an example. Identify the oxidation number and coordination number of the central metal ion in the following coordination compound. And when 1 mole of this compound is dissolved in water, what ions are produced? First, let us calculate the oxidation number of the central metal ion, which is iron. We have 3 potassiums. Each of the potassium has an oxidation number of +1. We have 1 iron with an oxidation number, let's assume, as X. And we have 3 oxalate ions. The charge on the oxalate ion is -2. If you add this all up, we should get 0. If we solve for X, X is equals to +3. That is, the oxidation number of iron in this coordination compound is +3. Next, let us calculate the coordination number of the central metal ion. For that, you need to know the identity of this ligand. That is, what type of ligand is oxalate. And you are supposed to remember this. Oxalate is a bidentate ligand. That means it has 2 donor atoms per oxalate ion. And we have in total 3 oxalate ions, which means in total we have 6 donor atoms, or we can say that the coordination number of iron is 6. Next, let us answer the third question, which is when 1 mole of this compound is dissolved in water, what ions are produced? Based on the format, the ions that are outside the square bracket ionize. Therefore, when 1 mole of this compound is dissolved in water, the 3 potassiums that are outside the square bracket ionize to form 3 moles of K+. And to maintain the charge neutrality, the complex anion should have a -3 charge on it. This is an example in which we have a complex anion and a simple cation.